Okay, your question was whether you have to put other design process, right? You have to provide the process diagram only. Okay, you don't have to provide all these pumps and um, the other details. You don't have to. You just the process diagram. Okay, so like okay, you have pre-treatment, screening. Then you have what say those grid chamber. Then you can have another big chamber and those sort of things. That's the major ones. Okay? So you don't have to have other details. So just pump or electrical details you don't have to provide. Just a plain layout diagram that I usually present in the class. Yeah, those sort of things.
I have to only share them in the mail.
Okay. Did is it clear?
Yeah, yes, sir. Yes.
Mm.
There
Hi,
is two sort of
Jimmy.
details in the one information is data should be used to design.
Sagar, it's not clear to me. Your sound is coming very low from far behind. Can you speak with your mic near to your mouth?
Yeah, sir. Do you
Okay.
listening?
Yes.
Are you
Yes.
listening
That's
now?
clear now. Yes. Yes. Please go ahead. Yeah. You are muted now, Sagar. Sagar, I can't hear you. Can you repeat your question? Okay. Yeah. Yes. Please fix properly, and then you can ask me. Maybe you can type the question here. Hi, Sean.
Hello, Shahrukh. Hello, everybody.
Yeah. Hi, Jinming, and hi, Anmar.
Hello, Professor.
Hello,
Uh,
Professor.
Thanks for coming. So let's wait for some few more minutes so that more people can join. Hopefully, maybe 2 or 3 minutes. Yeah, can you see my screen?
Yeah.
Okay, great. For a few minutes, then you will start. Okay. Okay. Maybe we should start now. I think we have a long. Yeah. Hopefully some more people will join. Okay. So I have some questions here from Saga. Yeah, we will. I'll address you at the end. Okay, Saga. Because we have. I kept it towards the end. It's question and answer session. And then initially I'll just briefly review of what you have to do. Okay. Good afternoon, everyone. Welcome to this consultation session for block 2. So this will be particularly consultation session for assignment tasks 2. And yeah, so Sean is also here. So Sean, do you have any announcement to make, or?
No, just yeah, we can have almost 1 weeks later for our assignment 2, and then we have module 3 in 2 weeks. So it's time to finalize our last module. So today is the very important session for your assignment 2. So ask a lot of questions to Sharu. That's what I want to say today.
Thank you, Sean. Thank you.
Thanks.
So, okay, let's start. Oops. Okay, so this is today's brief outline. I will just briefly review the design calculations that you expected to do in this report, and some of the common questions that students have been asking from this time and also from the past, and some of the features of a good and bad report related to this task, and then here I can have finally some questions and answer. Okay. So yeah, some of the common questions I haven't received much this time, but if you have any questions related to this one, so the one that people used to ask is the actual wastewater treatment process versus the scenario. So the actual treatment process in this current thing is the scenario that we provided is a bit different. Okay, so we assume that there is a let's say the conventional activated slash process is already there in the existing treatment plant, and that we are supposed to design and compare how the you have to of course design the activated slash process, conventional activated slash process, and then also design at the same time membrane MBR process. So in that way, and both you compare, like in terms of energy, in terms of space required. So mainly two things that you want to compare is the energy and the space required, because that's the major advantage of providing MBR. Okay, MBR, as you introduce, the other advantage, of course, you increases the quality of the effluent that you discharge, because the treated water quality will be very good if you use MBR. But there's let's say a penalty for that. So that's the energy penalty is there. So you'll have to work out how much more energy it consumes compared to the activated starch process, and also how much footprint is reduced, because when you when you provide the MBR, then some of the process can be removed from the activated slash process, and then so in that way how much you can reduce. Okay. So anyway, the actual scenario is that the current treatment system is a conventional activated slash process. So that's how you have to describe in your report. And some students used to, in the past, used to provide this kind of provide process diagram, just paste it from the website, and sometimes even without any reference. So please do not do that. That will because we cannot give marks, those sort of things. You have to, we strongly encourage you to prepare your own process diagram. Okay, it can be your freehand sketching, that's fine, and then scan it and put it, or that you can do a good line diagram using even PowerPoint or whatever you feel it convenient, AutoCAD or whatever. Okay, but just make an effort to draw your own diagram. If it's beautiful, that would be even good. Okay. So just simply paste from the others. Okay. And then the some of the issues in the past was the unit of the sludge yield. So it is usually sometimes given in terms of kg suspended solid per kg BOD. So that means actually sludge yield, the definition is that how much sludge is produced per kilogram of BOD, right? How much kg of sludge is produced per kilogram of BOD. So that is that definition, okay? But some is that sludge is in terms of the MLSS. That's what we measure in the bioreactor. So MLSS means, it's a mixed liquid suspended solid. So ML is basically referring to the MLS concentration, okay? And some students used to ask about whether when you do this calculation for volume of the reactor, volume of the reactor is given by this equation, if you remember. The BL, that is the kilogram of BOD, so that's the BOD loading per day that's coming to the treatment plant, and sludge yield, and SRT, that's the sludge retention time, divided by the MLS concentration. So that MLSS concentration is not the BLSS concentration. Okay, BLSS means the volatile suspended solid. So that refers to actually usually the active bacterial mass in the bioreactor. But for our calculation, we use MLSS, not the BSS. Any question on this? So you can interrupt me anytime, and then I'm happy to answer your questions. Okay. So the calculation is done for energy, because mostly students get a little bit confused with the energy calculation. So I'm just repeating some of them here. So when this the equation given in the slide, and then so so you'll have to first work out what is the SOR, right? The specific oxygen ratio that's given by this equation. So in this equation, you will find AOR. So actually, it's the average oxygenation requirement, right? So usually, this should be the peak AOR they have to use, because in the question you will have given what is the peak factor. Okay, so since peak factor is given, you have to use that. If it is P 1.4, 1.5, then you have to use 1.5 of the peak AOR. Okay. And all these other things are given, beta and what's it, the alpha factors are given, so you'll have to just substitute this. And so power required is calculated using this equation. So power required for aerobic bioreactor in terms of kilowatts, so will be oxygen required, right? So how much oxygen is required within 24 hours, so that's 24 hours here, and that is per day. And the aeration efficiency, so aeration efficiency is given in terms of kg of oxygen SOR per kilowatt, so watt hour. So which means, like, how much efficiency means, like how much, if you input 1 kilowatt hour of energy, how much energy, I would say, how much oxygen, though that is really consumed by the bacteria, is provided by 1 kilogram of. So that is the aeration efficiency. Okay, so this is given, and so when you calculate this, then you can just get how much the estimated power required. Now, specific power. The specific power should not be confused with specific energy. Okay, so specific power is usually a guide that you can use later on. Okay, so you worked out how much power is required, and also you also worked out already how much volume of the reactor you require. So when you divide the total power required divided by the volume of the reactor, then you get, okay, how much power I should need if my volume of reactor is this much. So those sort of this is like a thumb rule. So this is what you want to get a thumb rule from your own calculation. So if you get, say, for example, 10 kilowatt of the power, and the reactor volume is 100 meter cube, that means, like, for every 1 meter cube you require around 0.1 kilowatt of power. Yeah? So that kind of easy, handy the data for design data that you can generate. So that's the reason for specific power. So the energy required will be, how much power. Then power is the rating for that equipment, right? So when you use for 1 hour, say for example, that becomes into 1 hour becomes kilowatt hour, say. Okay, so that's the energy that's consumed. So the total energy required per day will be given by this equation. So there's the power that we already calculated here. So that's the kilowatt hour, and 24 hours per day, right? So 24 hours per day. So that will be the total power consumed by the plant in a day. But we want to know how much, because that power, just mentioning the treatment plant, it doesn't mean anything, right? So treatment plant capacity can vary. So in that way, we want to now bring down to a smaller number. So which means that comes to specific energy required. So how much energy is required when you treat 1 meter cube of water? Okay, so that's the specific energy required. So that will be the total power consumed by the plant in a day divided by how much water is treated per day. So that gives you this usually the average dry weather flow. So the average the treatment that you have done in a day. So that will give you the total energy, specific energy consumption per meter cube. Okay. Any question? Okay, Saga, you want to ask any question? No?
No, up to now.
Okay. Okay. So seems no question. Okay, so now you'll have to do. So some questions students ask: is area and energy calculation adequate for comparison of uh, conventional activity slash versus the MBR? Yes, that's correct. The finally what we want is the major thing that you want to show from your calculation is the area versus and the energy, yeah, for comparison between the conventional activity source process and MBR. So something like that. This kind of this table summarizes, yeah. So you have say for example, these numbers are very indicative only. Okay, it's nothing, not from your calculation. So how we want you to present is like, okay, total bioreactor area. Okay, of course you have to show all this calculation step in either in the appendix or in the main the report. So how much bioreactor area is required, then how much the secondary clarifier, the area is required for the secondary clarifier. Okay, what's the area for the membrane zone? Okay, and then that gives you the total area of the treatment plant for the conventional activity research and the MBR. And then then the next comparison will be the energy. Okay, so how much power is required for the conventional activity slash process or MBR, then power required for MBR, okay, and then power required for the total required for the plant, and then gives you the total energy required. Yeah, this is the total energy required divided with what will be your treatment capacity, and that gives you the energy consumption. For example, MBR may give you around 1.7 kilowatt hour per meter cube, and I mean from this. So, but from your own calculation, it may be different, it should be different. And then yes, for conventional activity research process, it is much lower. So you can see compare the energy, specific energy consumption here. It's much lower for conventional activity slash process compared to MBR. Okay, but look at the area here. The area is much more for the conventional activity slash process compared to MBR. So in a way, for MBR we have area saving in terms of area, okay, plant area footprint, but we have to, but at the cost of the energy. Okay, so this is what you have to present in your calculation report. Any questions? Okay, so some of the design parameters here we can just review. So design parameters for activity sludge process. Okay, when you design the bioreactor volume, so what we need is the volume of the aeration zone. That's what you have to calculate, and the volume of the anoxic zone. So you first calculate based on the equation the total volume required for the bioreactor, and then the let's say the retention time for the retention time for the this one will be given separately. Let's say the aerobic zone will be given. So based on that, you can divide how much anoxic, let's say, aerobic zone is required and how much anoxic zone is required. And as you know, the reason for anoxic zone is basically to have denitrification. If you remember from the previous class, you have to have a denitrification. So in the bioreactor, aerobic bioreactor, what happens is the ammonia will be oxidized. Yeah, ammonia will be oxidized into nitrite and nitrate, right? NO3. So finally, you have a nitrate that goes to the then let's say, and some of them will be returned back to the anoxic zone. So that nitrate, which has oxygen NO3, and then and the anoxic condition is such that there is no oxygen, and but there is a plenty of BOD there, and there is certain type species of bacteria. They want to live it. They want to let's say they are living, and then they want to use the BOD for their food, but there is no oxygen, right? So there's no oxygen. So but these microorganisms have this capacity to strip the oxygen from the nitrate, because nitrate has oxygen NO3. So they will take the nitrogen, they will take the oxygen from the nitrate, and then use it for their oxidation of the BOD, and then generate their energy. And then when you do that, then nitrogen is released. Okay, so that's why you have nitrogen going out of the system as a nitrogen gas. Okay, so that's the reason for the anoxic zone. And you have a BOD concentration. So BOD concentration is, of course, the amount that's present in milligram in a liter of water, or kg per meter cube of the. So these are some of the units that you usually, when you do the calculation, big one, you use kg per meter cube, right? And BOD loading. Okay, BOD load is how much. BOD concentration is how much BOD is present in a liter of water, wastewater, where BOD loading is how much mass of BOD that is being loaded to the treatment plant, the total BOD that you are loading to the treatment plant. So that will give you BOD mass, my kg per meter cube, how much is contained in the volume, and the total volume in the treated in the treatment plants. That will be the average dry weather flow, okay, meter cube. So that gives you the total BOD loading. And MLS concentration is basically, as you say, I'm saying, is activated microorganism in the biological reactor. How much activated? Because when you do the aeration, so this MLSS is formed because to make the bacterial mass will grow. Okay, so that's and majority of the actually MLSS is the microorganism. And SRT is the sludge retention time. So or we are sometimes use mean cell residence time. It's either in days or hours, and is basically the definition is that how long the sludge that MLS that is formed is retained in the bioreactor. How long? Because after some time you cannot keep all the time that sludge. You have to remove from the system, because after sometimes the sludge will be formed, but there is nothing inside. BOD will be already consumed, and whatever BOD that's not consumed, which is not non-biodegradable, will be left on it. So that has to be removed from the system. Okay. So that how long it takes out, how long that sludge remains in the system, that gives you the sludge retention time. So sludge yield, as I said earlier, is the amount of sludge that is generated per kilogram of BOD that you put in. Yeah. That's at the end of the SRT. So when you remove from the system, when you remove the MLSS from the system, okay, sludge from the system. So that is the that is the sludge yield, means how much BOD you put in and how much sludge is from. So that is the calculation that you have. You don't have to make this. It's usually it's given, and then yeah. So, but the definition is that it is how much is generated per BOD of kg of BOD. Okay, so the now this is the equation that you use for the reactive volume, the total bioreactor volume that consists of both anaerobic, anoxic and the aerobic zone. So the total BOD loading, yeah, the BOD loading is at that how much kilogram of BOD per day. A sludge yield, so that is the kg per MLS as kg MLS per BOD, and SRT, that's the sludge retention time by MLS concentration. So now when you, so as I said earlier, volume of the reactor is equal to anoxic volume plus aerobic volume. So aerobic volume can be calculated by what's this total SRT that you are doing, which is the one that you use here, and the aerobic zone SRT. So if you do that, then that gives you the amount, the volume required for aerobic zone, and the rest will be, of course, the anoxic zone. And BOD loading, as I said earlier, is BOD, let's say, concentration multiplied by your the treatment capacity. There's the amount of wastewater coming to the treatment plant. And you have to do the calculation for clarifier, how much area is required for sedimentation now, the primary the secondary clarifier. So how much area is required for sedimentation tank. So this given by this equation, solid loads, okay, how much solid that you're putting in, that is the actual MLS concentration, because MLS is going to the sludge that is discharged, wasted, is going to the sedimentation tank. So that is the incomes kg per hour. And then what is the allowable maximum loading rate? So usually this is the design guide that you'll have to use. Yeah, okay? And how much number of clarifier you use? Usually minimum 2 is required, because as I said in the class, if you just have only one, then during the time of maintenance, then your whole treatment plant has to be shut down. So you don't want that to happen, because wastewater will keep coming, right? So it's always you have to have at least 2. So you can have 3, but yeah, at least minimum you have to have 2, so that one is always available for the operation continuously. Okay. So solid loads for this one can be calculated using the maximum flow rate and the MLSS concentration, I say. Yeah. And then you have a maximum flow here. Usually maximum flow we use for here in the calculation, because when you design the treatment plant to take the load for that maximum capacity. Okay, because the water will keep varying in the day. In a day, in the morning, there will be quite high flow, because everybody is using the water. And maybe during some time of the day, it's very low, because everybody, only few people are using. So in that way, there's a fluctuation in the water usage. So average is the total in a day that you are talking about. But the treatment plant will not receive average, right? It will receive, sometimes very high flow, sometimes very low. So your treatment plant should be able to design. You have to design in such a way that the treatment plant is able to take the maximum load. So that's why you have to use the maximum loading flow rate here. So how do you get maximum flow rate? That is the peak weather flow, wet weather flow plus return activity / process. So usually during the wet weather flow or wet weather flow means when there's a lot of heavy rain, and then so the additional water can come to the system, okay, through leakage. And sometimes in some countries, the storm water is also mixed with they have the similar line with the same line with the sewer lines. So in that way, the flow rate may significantly increase during the wet weather. So that's why you have usually a peak weather flow rate is there. And return activity / process. When you have here, for example, remember when you do the sedimentation and then you have sludge, that's still active, right? That sludge you have to, if you don't return to the system, then what can happen is that your bioreactor will be having less and less sludge, and then it will take more time for the bacteria to grow. So in that way, you cannot maintain the the required amount of MLSS concentration in the bioreactor. So how we do that? We do that by returning some of the activated waste sludge. So usually that's around the same flow rate as that's coming in. Okay. So that will be returned, and then the rest access will be removed from the system. Okay, and that goes to the treatment plant. Also the secondary treatment plant. I'm sorry, that goes to the anaerobic process where the sludge is further treated. Okay, so that is the return activated sludge process, and that usually is around one dry average dry weather flow conditions. Okay, so peak factors can be usually given 3. Okay, if it's given 3, then you can use 3 times the average dry weather flow rate, and then uh, return activated sludge is also around 1, usually taken at around 1 average dry weather flow. So in that way, your maximum flow rate in this case would be around 4 times the average. So which means you cannot design a treatment plant for just one average dry weather flow. Okay, even though your treatment plant capacity is say 1000 meter cube per day, right? That is the average treatment plant, but that treatment plant has to be designed to take at least 3 times that capacity. Okay, any question? Okay, so MBR, now comes MBR. So this is quite straightforward actually. So total membrane area required for the MBR will be the peak wet weather flow. That's at the peak time when you have a lot of let's say that the maximum one that we're talking. This maximum is different from a little the earlier one. Okay, so this will be the just peak weather flow. Not the maximum, because there is no return activity sludge in this case, and divided by the peak water flux, membrane flux. So this flux is how much amount of water that you can produce from 1 square meter of water membrane in 1 hour, right? So that gives you the total membrane area required. So once you have total membrane area that you require, then you have to work out how many modules are required. Yeah, so each module may be a few 15 square meter, 20 square meters. So depending on that, you can work out how many modules are required, and then how many cassettes are required, because membrane may be made of many let's say cassettes, right? So you have here, for example, this is the bundle, right? Rows, and we have membrane modules here, and they are combined together, and then all these are stacked together to form a cassette. Okay, so that how much the cassettes is required. So that will depend on total membrane area required, but divided by how many cassettes are there in each membrane. Okay, each module. So the calculation for the MBR, someone asked me in the email, but one of the students asked me in the email, but before somebody's waiting here. Okay. Someone asked me in the email about this about the calculation for MBR zone. Okay. And yeah, before I could respond, but I accidentally deleted that and I couldn't retrieve. So I don't see the name of that student. Yeah, I couldn't really recollect that name. But anyway, so what he asked was about the membrane MBR zone. So okay, here the calculation for power requirement for radiation requirement will be almost similar for MBR when you're working on. But MBR, when you have MBR, you have aeration zone, also MBR zone. Okay, so you have to calculate separately, but you will have already calculated for aerobic zone, so you can use that same data. Okay, for when you calculate the MBR, what's it, aerobic zone. But when you do the MBR zone, then you'll have to use the different the parameters that's given. So if you use the different parameters that you will be given, other things will be almost similar, like Dio said. Only time Dio zone will be different. So that's how you can work out. They do the calculation. There are some other correction factors that you have to take, but here for the timing, for this simple calculation, we haven't considered that. But because BOD concentration may slightly change in the MBR, zone, so we have to take that correction factor. But yeah, for the time being, yeah, you don't have to worry about that. Okay. And yeah, so these calculations are same like we gave earlier. Yeah, so first you calculate the SOR, and then you work out the oxygen. You have to work out first the oxygen, the oxygenation requirement here, right, per day, and based on that you can work out SOR, right? SOR. Sorry, it's not like that. So you work out this one first, and then you get this, yeah, because this one is given. So we can find how much oxygen is. So this is the average oxygen required. Okay, how much oxygen is required per day. Okay, so that will depend on how much BOD you are putting in, and then the SOR here. Okay, and then gives you the total power will be what is the oxygen required per day, and then what is the efficiency of the oxygenation. So that gives you the power, and a specific power will be power divided by the volume of the reactor. Okay, so this is just a repeat from what I said earlier. And the total power required for MBR zone will be aeration, the power required for the aeration zone, power required for the MBR zone, okay, to provide the aeration, and then flux required, the power required for flux management. So flux management is given by this equation here. There's a complicated way of doing the calculation to find the power required, because when you do that, if you remember, in the bioreactor, when you aerated bioreactor, we provide lot of fine bubbles, yeah, so that oxygen dissolves in that, yeah? So that oxygen dissolves in water, and then it's made available for the bacteria to, to digest the organics. But in the flux management, what we have is we provide coarse bubbles, larger bubbles, because if you provide small bubbles, the bubbles will travel very slowly up. So it will not provide that force to remove the dirt that is deposited on the membrane surface. So when the membrane is filtering, there will a lot of deposit on the membrane surface. So we provide a large air bubble, so that this will, when large bubble travel faster, it has a higher force, and then it will scour, or it will just remove the dirt, and in that way you can maintain the flux without fouling. Okay, not without fouling, but fouling will be there anyway, but at least the flux reduction will be slow, rate will be slowed down. So in that way you have to do this flux management, and then there's the energy required for that, because you have to do a separate aeration for that. So usually, as I said, you can do a complex way of doing, because that depends on what is the size of your bubbles that you want, what is the rate that you want to apply. But for your simplicity, we have provided this. I forgot to change this one. This in your assignment, it should be 0.1 kilowatt hour per meter cube. Okay, we have provided you average of. So for example, if you treat 1 meter cube of water by using MBR, then the energy that's required for flux management is around 0.1 kilowatt hour. Okay, so that's what you have to use here. So this will be 0.1 kilowatt hour, not 0.5 per meter cube, and multiply by how much you are treating. So you're treating this is average dry weather flow is the amount you are treating a day. So that gives you what's the power required for flux management. Okay. Okay, somebody asked me some question. Do we have to design both? Yes. Sagar has asked me, what do we have to design both CA, CAS and MBR? Yes, I said you have to design both. First, you have to design CAS, okay, conventional activity slash process. So how much volume is required for the reactor, how much area is required for the reactor, okay, because the depth is given. So based on that, you can work out. Then you can work out how much area is required for um, the surface area required for the sedimentation, right? The secondary clarifier, right? And now that one you have to later compare with the MBR. Then for MBR you have to do separate calculation, but some of the calculations you can use from the MBR, from the CAS, because MBR is a combination of CAS and the membrane. Okay, so the say for example aeration zone. For this one, the power required for the aeration zone will be same as the CAS for both the CAS and the MBR. Okay, but for CAS there will be no flux management and no MBR zone power required. So this will be additional. Okay, so when you compare with the, so this is what you have to do the calculation. Okay. So this is how you will use it for the calculation of power for the MBR. So total power required will be power required for aerobic bioreactor, MBR zone, and the power required for flux management. So again, the other one you have to do is you'll have to do the process design, right? So this is some of the options that you can provide. For example, we discussed this one earlier. So you have something like this. Okay, you don't have to give other detailed design like pump and those sort of things. We don't want that. Okay, so we want just a process. So this you have primary treatment, yeah, CAS, yeah, conventional activator slash process. Then you have clarifier, and it may be some for by sand filtration. Then you can do advanced membrane process, then disinfect, and then we can use for water reuse. Okay, so this is one option. The other option is you have CAS, then you provide MBR, then you can provide this advanced membrane process or disinfect, and then after water reuse. But the question is, can we use this one for direct drinking? No, we can't use it for drinking. But no, in terms of water quality, is quite good. But still, there are issues that have not really. One issue is still whether there's some contaminants still there, like the pharmaceuticals and very minor concentration that's still not removed. And also there's that people, if you must have touched in the block 2, my block 1, where people still have that yuck factor that they are not able to accept this water. So this is one of the options for non-potable purpose. Okay, indirectly drinking, right? Non-potable. So this is the example that we'll see in the next slide, that in the Central Park, where you treat the water to very high quality and then you use for non-potable purposes like toilet flushing, laundry, then irrigation of the plants, right? And irrigation of the lawns, then fire hydrants, and then cleaning the floor, yeah, the car park, and then again for the cooling tower. So there is, but not for direct drinking. Okay, so but now this is the option for, this is one option that you have to take. The other option that you have to provide is how to augment the drinking water. Okay, augment the drinking water. So you can see the examples in Singapore, where they have very advanced treatment systems, and the advanced treated water is then mixed with the mixed and stored with the fresh water reservoir, and then they again tap it, then again treat this at the same process like a waste, the fresh water, and then supply it for drinking. So indirectly they are drinking that, yeah, indirectly they are drinking, so they are augmenting the fresh water source. So this is one of the things that you'll have to work out in your process diagram. Okay, so you have to provide two options. So this is the example of the Central Park, where they have screening. Okay, they produce wastewater from the apartments, commercial, everything here, and then they treat first. They do screening, then they go to the anoxic tank, and then it goes to aerobic bioreactor, and then there's some chemical processing here, and then go to membrane bioreactor, and then they are treated by ultraviolet rays to kill any bacteria that's, and then and most of them are treated by reverse osmosis, or they are just now as far as I know, we were told that the reverse osmosis is treating 100% of the water, and then it goes to the reservoir and chlorination, and then they supply back to the residents here for non-potable purposes. Okay, so this is how you are going to design similar kind of thing. But it's not only this, you can provide other options as well, other oxidation process as well. Okay, so the scenario of your assignment is that you have a current Malabar wastewater treatment plant, which is made of conventional activated charge process, and there's a proposal to upgrade this to a treatment system and to using MBR. Okay, so this is how scenario is that, okay, you have a conventional activated slash process, and then you want to propose it to upgrade to MBR. Then you want to compare what is the energy required and the space, because how much space you can reduce. So if that's not the case, then what's the purpose of MBR, right? So of course it will produce the effluent good, better quality, but the other advantage is that it will significantly reduce the space required. Okay, so that's how you have to consider. And also, as I said, options for non-potable purpose use, that and then indirect potable water reuse. Okay, for water augmentation. So this is the current one treatment plan, and then you want to do the calculation for this, and then you propose MBR and do calculation for that. So that's how you have to present. And your assignment task should be around 10 to 12 pages. Okay, it's written around 20 pages, but don't go to that extent. But we don't really care about actually the pages, but the shorter you write, the more concise is better it is. Okay, but I would advise you to limit to within 10 to 12 pages as outlined in the subject outline. Okay, given in the subject outline. And actually, then you have to prepare a very professional report, assuming that you're a consultant. Actually, if you in the scenario, if you look at, you're being engaged by the Sydney Water as a consultant to, advise them. Yeah, and that advice is in the form of the report that you're submitting. That, okay, uh, if you upgrade to the MBR, and this is the advantage. This is much is how much you have to energy you have to put, but and how much space you will save. Okay, and report should be quite details should be scientific, okay, and reasonable as possible, and back with the references. Okay, so you don't give your own judgment, you have to give a reasonable scientific statements, and then backed by the references. Okay, and report should be informative and clear. So how a consultant, if you are just imagine that you are being paid to do this. Okay, so if you provide a crap report with your then will the client accept it? No, right? So that is, yeah. So now how I will look at is, I will be assuming to be that you are boss. So okay, we're in a consulting firm, and we got this contract from Sydney Water as a consultant, and then I, as a boss, engaging you to prepare that report, and then first you're submitting the report to me before we submit to Sydney Water, and then see how. Then I'm going to assess your report and see how whether this really the report that you prepared is suitable for Sydney Water. Okay. And we have provided the format. Okay, we have provided the format in the assignment. If you go to the canvas and if you click the assignment, the report sample is also given, and also report the format is given. So you can use that. And that's one of the guide that we have given, or maybe you can use your own format. That's fine as well. So, but it's easier for you if you use the format that we have provided. Okay. So some features of good and bad report, that's based on the experience from the past. So please provide a clear cover page, because if you don't have any cover page, then you don't know what this report is about. Okay, so the cover page should have clear titles and author details, and you can put the assignment cover. Okay, and then, or if you have no title, or some titles there, some title is not there, but the author name is there, but there is no title, so it doesn't make any sense. Some students just write the assignment task too. So assignment is just assignment, but it's not the project title, right? Project title is not the assignment. Yeah, so but project title is a part of this assignment, so main thing should be a project title. Okay, and summary, executive summary, or the abstract should be clear and concise, and that covers the report context, objectives, findings, and conclusions. So it should be summary of everything should be there. but some students, if they may, some even doesn't submit abstract, so then you lose the mark. And some are very short and very generic, like it doesn't, instead of the summarizing what you have done and what you have found out, but you may just be very generic, but that will not give you the marks. Okay, so that's the feature of bad report. So table of content should be there, and it should be all linked, so that when you click, we go to directly to the content that we are looking for. Okay. Background and objectives. So here it should also be very clear, informative, and of course clear, but you can be succinct. Okay, very summarized, not very detailed and very long thing. Okay. And even sometimes students just to discuss things they are not out of context, and then discovering very much about other treatment plan that's not relevant. So don't just to fill up the pages, don't write anything like that. And current wastewater treatment plant of this is what I was saying earlier. You just try to cover the very important ones, what is there, and then you can, some of them you can make out, but but relevant ones. Okay, relevant ones. And you can provide the detailed diagrams. Diagrams are given in that scenario as well, but you can draw your own diagram and provide as well. Okay, and not just very submitting, just copy pasting diagram from outside, and then no clear information, very fictitious, and then poorly drawn diagram. So that should not be there. And alternate wastewater, so this should be also very clear. A process diagram, as I said, please draw your own process diagram, not just paste from the website, because you're designing, you're proposing your own process. And all this design calculation should be included in the, either you can do, if you're doing in the Excel sheet, you can submit as an appendix. You can do free diagram, I mean free calculation in your plan, then you scan this one and put. So it doesn't matter. So whatever, you don't spend waste your time typing all this equation and then showing all this calculation steps. That's not necessary. You don't get any additional marks for that. Okay, you can just write in your freehand, and then paste, scan it, and you submit as appendix. And also you have to provide why all the water quality parameters, why you're choosing this design parameter, why you're just choosing this process, and then you have to explain each process and how it helps. Okay, so if all these things are not there, then the features of a bad report, and then you not get marks. And drinking water augmentation also is similar. Okay, you have to provide your own uh, process design, clear, and then show them you have to see whether this is safe to drink, because is it safe to, of course you're not drinking directly, but we are mixing with fresh water and then you're treating it again and drinking, right? But is this safe way to do it? Because that's how you have to provide the process design. And if you have already described some of the processes earlier, then you don't have to repeat it. Okay, here, so if you provide additional process in this case, then you can describe, and then you for other process which you already described earlier, then you can just give a reference that, okay, as described earlier, or something like that. Okay, now conclusion should be should be very summarized one, report very succinct, clear, and finding you like what is your findings, and then your recommendation. Okay, because recommendation, because you are submitting the report to Sydney Water, so there should be some recommendation. Yeah, and also you can find what are the limitations of your report. Okay, and your table and figures should be all included. You can what say table should be clearly named. Okay, title of the tables and figures should be there. Okay, numbering, including the numbering. So, and the references, a minimum of 10 references should be there. Please use referencing software, either EndNote or some other any other software that you're using, but just don't use like normal thing, because this is one of the process of for you to learn. So we have referencing software. Please use it, because it's free. You can adopt, you can download from the UTS website, and how to use this referencing EndNote, for example. It's already given in the canvas. So there is a video there, and if you don't know how to use, just watch that video. So now is the question and answer, and if you have any questions, yeah, I'm happy to answer related to the whatever I've covered or anything that I may not cover. If you have additional questions, yeah, please free to ask.
So, Professor, I have a quick question.
Okay,
So
Jimmy, go ahead.
I see two reports example in the module. So both the example is good, right?
Yeah. So they are both are good examples. So I've just I think I didn't provide the bad one and the good ones separate. Both are good one. One is from last year, and another one is from before last year. So that you can have.
Yeah, because someone it has a barely past example. So so
Yeah. So that's why I to give you more varieties. I provided from both the years.
okay, thank you.
Okay. Okay. Any other? Is Sagar? Did I answer all your questions?
Yes, sir.
Okay.
If I have any question, I will directly email you. Is that okay?
Great. Okay, that's fine. Yeah.
Thanks.
Okay. Any other? Chen, do you have any questions? Or Anmar?
No, I don't. Thank you, doctor.
Okay. How about Chen? Do you have any questions?
Doctor, if we have any questions in the future, we can email you, right?
Yeah. Sure. Anytime.
Uh,
Yes. Yeah. I'm happy to answer. Yeah. That's fine. Anytime you can send me email. Yeah. To
okay,
clarify.
thank you.
So if you want to have face-to-face meeting first, also I'm happy to organize that. Okay.
Thank you.
There's some question here. Okay.
So can we
Okay. Go ahead, Jimin. Yeah.
so can we email you in the MS Team or just the Canvas?
Yeah. Anywhere, MS Team or from the Canvas or from just email, whatever. That's fine. I will respond. I have all the access. I have access to all.
Okay, thank you.
Okay. Yeah. Maybe it's better to email because sometimes I forgot to see the team because team doesn't really give the when you're in the when you're in the just in front of the computer, then you can see that something is coming from the team, but when you're not there, then it doesn't really pop you up and then remind. But email I keep constantly changing checking, so it's better. My best option is email.
Okay.
And so looks like if you don't have any other questions, so Sean, anything to?
I just want to say have a great long weekend.
I also wish everyone a happy Anzac Day on Monday. Yeah, I think but COVID is really raging. Many relaxed now, but yeah, I think we have to take care of ourselves. Yeah. Okay. If you don't have any questions, yeah, please email me if you have questions later on. Yeah. Thank you very much for coming, everyone. Yeah. Have a long weekend. Good weekend.
Thank you,
Okay.
Thank you.
Professor.
Bye-bye.
Yeah, thank you,
Thank you,
boss.
Thank
everybody.
you,
Thank
Professor.
you.
Yeah.
Bye-bye. Bye-bye. Yeah.
Bye bye.
So
Yes, Sean. Yeah.
I think can you start the recording now?
Okay.